Okay, so I left you thinking about this spectrum of the atomic hydrogen emission line at 21 centimeters from a spiral galaxy. Okay. And first of all, asking about this kind of why there are two sort of velocity components, if you, is the phrase we would normally use. So there seems to be one that's more to the lower velocities would be blue shifted, higher velocities would be red shifted in the way that the Doppler shift works. Now, there's one thing I told you about a spiral galaxy, and that they rotate in an organized fashion. Okay, so there's a well-defined axis of rotation, which means that on one side of the galaxy, there will be gas that is coming towards us due to the rotation of the galaxy. And on the other side of the axis of rotation, there will be gas that's moving away from us due to the rotation of the spiral galaxy. So again, the scale is a bit difficult to read here, but you can see that the sort of velocity split between these two components is, what's that? So that's 250, so that's 125, so probably about 100 kilometers per second or something like that. Okay. And we'll see later that that's the sort of typical rotation speeds for galaxies. So that kind of makes sense. Also here, I asked you about, why the whole galaxy itself seems to be up at this high velocity of 1500 kilometers per second. So that's the Doppler shift of, in a sense, all the gas in this galaxy is moving along at some high speed, redshifted away from us. As you may be aware, most galaxies have a redshift associated with them, that they're all moving away from us. We'll come back to this later in the module. But that's what's going on here. This is rather analogous to the sort of binary star issues that we were looking at. You can think of this as the velocity of the center of mass of a galaxy, and then these are the components rotating around it, around that center of mass. Okay. You can see that a little bit more in action in this. Apologies, it's a rather busy slide, so ignore all the details on the right here. Let me just talk you through what we're looking at. So again, this is on the top here, we have an image of a spiral galaxy. In the purple, we can see, in a sense, the sort of normal optical, sort of ultraviolet infrared bit of the galaxy, so the stars, if you like. You can see some spiral arms, I think, just about there. Okay. Now, the blue light that you can see way out, extending way past the extent of the optical galaxy, is the light from atomic hydrogen. See, it's in blue here, imaged by, again, the Very Large Array, the radio telescope in New Mexico. And this is a feature of the atomic hydrogen in galaxies. There's a lot of gas, not only throughout the disk of the galaxy, so that's what I said earlier, that the H1 gas makes up most of the mass of the interstellar material in a spiral galaxy. But also, it does extend way out past where the stars are. So there's gas out here, even though there are no stars. It's basically too low a density to form any stars, but it doesn't mean it's not there. It is there. The image below is the same data, but this time color-coded by the Doppler shift. So on the left side here, we have colored in blue, gas that is coming towards us. And on the right side, we've got gas colored red that is going away from us. Okay, so that means the galaxy is rotating around in this direction. And so that we can see gas is coming towards us on this side, going away from us on that side. That's the beautiful thing about a spectral line. You get information on the velocities as well as where the gas is. Okay, so that's molecular hydrogen gas. Sorry, atomic hydrogen gas. Now we're going to talk about molecular gas. So this is the sort of last of the sort of three main phases, if you like. We've gone through ionized hydrogen, atomic hydrogen, and now we're going to talk about if there's any molecular gas out there in interstellar space, and there is. Okay. Now, to form molecules, you've got to somehow bring two atoms, like two atoms of hydrogen together, and bring them together, make them sort of form a molecule, but also ensure that it doesn't get broken up again as a molecule. So in the conditions in space, then that means we need the gas to be very cold, and we also need quite dense regions of gas again in order to bring enough atoms together to form molecules. So we need dense cold gas to form molecules. Now, dense again will mean 10 to the 10 again. So similar to the H2 regions we talked about earlier, and there's a good reason for that we'll bring together eventually. And cold. Okay, so by cold now, this is much colder than the atomic gas, which was 100 Kelvin, so less than 30 Kelvin. These regions can even get down to sort of 10 or 20 Kelvin. So these are the coldest bits of the interstellar medium. So how do we observe these molecular regions? Well, now we have a bigger problem in that molecular hydrogen that is this cold basically does not emit at all any kind of electromagnetic radiation. So that means we can't observe it. Okay, so we're kind of stuck. The reason for this is that gas that's this cold, again, if we think about energy level structures in a molecule, molecules have them just like atoms. We certainly can't excite the sort of normal electronic transitions because, again, everything is much, far too cold. The electrons are not going to be excited into the upper electronic levels that are to do with the electron's orbital angular momentum. Now, molecules have other ways of, have other types of angular momentum. And one of those is the fact that molecules can rotate. So you've got two ends of a molecule, and a molecule will rotate. So it's got rotational angular momentum. So that's good, and that is quantized. But in order for it to emit, you need to have an asymmetric charge distribution across your molecule. Whereas H2, as you'd imagine, it's just the same charge on each end, then it's not asymmetric, so it does not emit. So we need to find another molecule that does. Okay, so we need to find an asymmetric molecule that is reasonably abundant that we could observe instead. And I'm just going to highlight one of them, which is carbon monoxide. Okay, so obviously you've got hydrogen, which is the most abundant element. Then you've got helium, but that's inert. So the next most abundant elements after that in the cosmos, at least, are carbon and nitrogen, oxygen. So you can combine those together in various molecules. But carbon monoxide is generally the most abundant and reliable one to use and convenient to observe. So this is an example of one of these, what we would call a rotational transition. So the CO molecule rotates. I'll show you a diagram in a moment. And again, just other molecules colliding into the CO molecule will cause electrons to get excited and sort of basically send the molecule into different rotational states. And it will again relax down by emitting photons. And the transition into the ground state of that rotational transition is at a wavelength of 3 millimeters. Okay, so this is a part of the electromagnetic spectrum that's kind of in between the infrared and the radio. So it's normally referred to as the millimeter wave part of the spectrum for obvious reasons. And basically the telescopes operating at these wavelengths are very similar to radio dishes, just a bit better surfaces. Now there are, pretty much hundreds of different molecules that can be observed out there in space. These clouds where molecular hydrogen exists, not only do they have CO, but all sorts of types of molecules are there. Other common ones would be things like methane and ammonia and water. So those are all hydrides of the common elements of CNO. You've got nasty things like cyanide. You've got quite complex molecules. People have found sort of quite long chain carbon molecules, simple sugars, and the hunt is on for even amino acids in space. So a lot of interesting astrochemistry out there, which again is another feature of expertise here in the Leeds Astrophysics group. So a lot of people studying different molecules in space. But coming back to our main purpose here of looking at clouds of molecular gas. So this idea about them not being destroyed. Okay, so if any ultraviolet radiation impinges on a molecule like CO or hydrogen, then there's enough energy in a single photon of ultraviolet radiation to basically break the molecule up again. So we need to shield our molecular gas from that sort of radiation, and we will sort of finish that story next time. Okay, so here's an example of what we're talking about. So here's the CO molecule. So you've got carbon at one end, oxygen at the other, +6 charge here, and a +8 charge here. So more electrons tend to swarm around this end than they do this end. That gives this molecule what's called a permanent dipole moment, and as it rotates, it's basically an accelerating charge then, and so it has the ability to radiate. Okay. But again, this rotation is in different quantized states. So this little animation shows you the fact that there are clouds of these molecular gases out there in space. So then this is a map of emission from this carbon monoxide molecule at that 3 mm wavelength, superimposed on a sort of an optical picture of the Orion constellation, okay, just taken with a small telescope. So this spans like tens of degrees. This is huge across the sky. So you can see that, you know, these molecular clouds, you know, in the Milky Way are kind of everywhere. And this is the Orion Nebula, the H2 region that I showed you earlier, just that little faint pinky blob there. It's the H-alpha emission from the H2 region, the Orion Nebula that I showed at the beginning of this lecture. And you can see there's a lot of molecular gas concentrated around there. And that's because this molecular gas is the raw material for forming new stars. So you need this cold molecular gas to collapse under gravity before you can form any new stars. And so you will find H2 regions and the molecular gas sort of opposite ends, often in the same location. Well, necessarily in the same location. Okay, so that's using 3 mm. Again, this is a spectral line to map out the emission. Again, the colors here are just false colors to represent the intensity. Okay, so let's summarize these 3 elements of the interstellar gas. So we've had ionized hydrogen, H2 regions. They arise when you've got massive stars forming, and they observed mainly through H-alpha and centimeter wave radio continuum, okay, the Bremsstrahlung mechanism. We've then looked at atomic hydrogen, H1, using the 21 centimeter spin flip transition. Okay, so that's radio as well. And this is the component that makes up most of the mass of the interstellar medium. So if you see ISM, it stands for interstellar medium. And then this H2, not to be confused with this H2, so molecular hydrogen has to be traced using a different tracer molecule like CO, observed. Most molecules have transitions in the millimeter range of the spectrum. And this is the material from which stars actually form. So there's a kind of a loop here, if you like, okay? So if you can sweep up enough atomic gas and get it dense enough, it'll cool down and form molecular gas. If you can get enough of that together, it will start to collapse under its own gravity. It will make some new stars. And then if any of those new stars are very massive and hot, then they will then form an H2 region. So there is a bit of a life cycle of the interstellar gas going on out here as well. Okay. So just another little exercise to perhaps give you some more little insights into the dynamic nature of the interstellar medium. It's not a sort of static situation out there. Then these phases are constantly being buffeted around by various forces, some of which are just pressure forces. So to give you an insight into that, then I'd like you to, again, apply some basic physics that you do know. So take the ideal gas law, PV equals nRT, where n is the number of moles in that equation, R is the gas constant. You can start from there and then manipulate that equation into a form that's got the number density in it. So number density, number of particles per meter cubed. Okay. And show that the pressure of a gas is just proportional to n times T, where n is the number density. Okay. And then if you go back and look at the typical parameters for H2 regions on molecular clouds, okay, show why we might expect that H2 regions, that bubble of hot gas like in the Orion Nebula, is actually much higher pressure than its surroundings and will expand into the surrounding, usually molecular material. Okay, so that's another little exercise for you to have a go at. In the next, where are we going next? We're either going to supernova or dust. I can't remember which, but we'll find out next week.